Okay, got it? He got it. GOT, right? GOT is got. All right. Now I'll write great orthogonality theorem for you, and then I expect some comment. Okay? I'll just write it down. Sum over R d ik mu R d mj nu R inverse is equal to G by n mu del mu nu del ij del km. It's a little different from what we had written earlier, isn't it? Right? So my question to you is, not now, try and work out whether they are equivalent or one is a subset of the other. What do you think? What we have written here, is it going to be the same as what we had written earlier, or is it going to be a subset or a superset? Which one is a superset? This is a subset, right? Because here we are talking about R and R inverse. There we are had talked about all R's. So now my question to you, and this is a homework problem, is can you get from here to there? So everybody has studied second law of thermodynamics, right? There are two statements, isn't it? Kelvin-Planck statement and Clausius statement. And it is very common to ask, can you prove that these two statements are equivalent to each other? Sucheta is amused. So here also, I want you to figure out by yourself, I am not going to help you with this, whether they are equivalent or not. Okay, fine. Let me see how far we can go in proving this. I suspect that I am going to run out of patience towards the end and then run through it quickly. At least let us begin. Okay. What are these? Mu and nu once again are two different non-equivalent IRs. Yes. What had we written earlier? H by Li, right? Earlier we had written that the order of the order is H and Li is dimensionality. So n mu, it is not just n subscript mu. It's just that my handwriting is not great. So G is the order, n mu is the dimensionality. Okay. So let us see. Of course, there are many deltas and all, but do not be afraid. How do you think we are going to reach the deltas? Can anybody make a guess? We have been talking so much about matrices. How do you think we are going to reach the deltas? Yes. Think of unit matrix to start with. So, isn't unit matrix made up of Kronecker delta? Right? Delta ij, isn't it? When I equal to j, then it is 1. When I is not equal to j, then it is 0. So that is how. That is how. And that is why we needed to develop that concept of A. Why? Because A, what is A? A equal to lambda into E. Right? Lambda into E means you have something that comprises of deltas everywhere. Now do you understand the relevance? Why out of the blue we had to derive all these two lemmas and all? Because we want to formulate our problem in such a way that we are going to have unit matrices. When you have unit matrices, then you have a very binary situation, 1 or 0, right? When I equal to j, then it is going to be 1, otherwise it is going to be 0. And then when you have this 1, 0 situation, then once again you can relate it very conveniently to a set of orthonormal vectors. Okay, that is why we developed this concept of A all this phi. That is what I want you to understand. Rest of the mathematics you are much better than me to work out. Okay, if you have understood this far, I might as well step down. Any one of you can come and do the remaining derivation. It's not all that difficult. But it's important to understand why out of the blue we invoke this matrix A, which is a constant matrix. Okay, because that is going to lead us to this orthonormal set of vectors. Okay. Now, with that background, let us be brave and tackle the problem. It's not all that difficult anymore. Okay. Now, so this has to be done in two parts actually. In the first part, I am going to develop this matrix A equal to sum over S ds x d S inverse. And what I want to prove is that A dr is equal to dr into A for all the symmetry operations. Understand what I am doing? I am going to write this matrix sum over S ds x ds inverse, and I am going to prove that this matrix commutes with all the transformation matrices that are there. Understand what I am saying? Right? And how is that going to be helpful? If this commutation is there, how is it going to be helpful? Don't have such short memories. What happens when a matrix commutes with all the transformation matrices in an irreducible representation? Then that matrix is a constant matrix, no? Why do you think I have written A? It's the same A. Otherwise, I would have written X or P or Q or Z. Okay? This A is going to be lambda into E. At the moment we reach E, see what I have? This A itself is a summation, right? Summation over all symmetry operations. I am summing over all symmetry operations. Okay? So that is going to be something like 0, 1, orthonormal vectors. Okay? But let us first prove whether this is correct or not. What I want to prove is A commutes with all the drs. Don't forget what A is. It is sum over S ds x dx inverse. So let us see. What is dr A? Can someone help me? Expand. Write down the expression of A and tell me. I will help you a little bit. Sum over S. That's easy. What is A? What was the definition of A? Sum over S ds x ds inverse, and I am left multiplying it by dr. So what should I get? Opposite? No, don't expect such fast results. What is the expression? Come on, that's easy. Yeah. And this is a course in symmetry. No, R is not equal to S. S is a general identifier. R is a specific identifier so far at least. Okay, so there is going to be S that is not equal to R also. What I am saying is, since it is a course in symmetry, and since de Broglie had said that nature loves symmetry, we also love symmetry. We are not unnatural beings. Yeah, exactly. R is a particular one. So what I will do is have dr ds, and then I have x. I cannot do anything about x. X is x. But then I have ds inverse. So it will look kind of nice if I write dr inverse here. Symmetry, like inversion symmetry. But of course, it is not enough if I write dr inverse and stop there. So I better write dr as well. Right? Agreed? What I have here is dr ds. What I have here is ds inverse dr inverse. What is dr ds? Now we are using a group theory. The symmetry operations form a group, right? So a product of two symmetry operations is also another symmetry operation, right? Symmetry operation number 1, symmetry operation number 2, and then third symmetry operation, right? Third starts with T, so I am going to call it T. And not really, just I made that up. I will call it T. What is T? T is equal to SR. Alright, T equal to SR, and dt is a transformation matrix corresponding to the symmetry operation T. And the reason why T is a symmetry operation is, which property of the groups tells us that T has to be a symmetry operation also? Yes? Closure, yes, closure. Understand what I am saying? So instead of writing dr ds, I am justified in writing dt, right, where T is another symmetry operation which corresponds to operating R and S one after the other. Okay? Will you allow me to write this as dt inverse? Just multiply together and see for yourself. Dr ds, ds inverse, dr inverse. Is that not E? Dr ds, ds inverse, forget this x, think that this x is multiplication. Dr ds, ds inverse, dr inverse. So first forget these two, ds inverse is E, then you have dr E, dr inverse, right. So what I am saying is ds inverse, dr inverse is nothing but the transformation matrix corresponding to the operation T inverse. Achal, comfortable? Okay, good. So how do I write this now? I can write this as sum over T dt x d T inverse dr. Mehak, does this look familiar? Sum over T dt x dt inverse. That is A. It is just that instead of S, we are calling it T. But as Shakespeare had said, what's in a name? Right? It is still a generic symmetry operation. Fine? Right? So it's A dr. Commutation is proved. Right? So if commutation is proved, then we know already from Schur's lemma number 1 that A equal to lambda E. What determines the value of lambda? Value of lambda is determined by the matrix X, right? Right? Because A, right? A equal to lambda E. Now, if X is some matrix and then if X is another matrix, you are going to get different values of lambda, that is all. The general form is not going to be the same. The general form is going to be the same, sorry, an extra naught. Okay? A general form is going to be the same, but value of lambda will depend on which X matrix you are using. Okay? So, now what we have done so far is that we have developed a perfectly general theory. Okay? Now, let us try to make it a little more specific so that we can actually get to great orthogonality theorem. So, what I am going to say is that X is of this form. Let us say this is the mth column, and let us say that very bad at drawing, completely unsymmetric. Let us say this is the kth row. What I am saying is I can choose an X. X can be anything, right? In the earlier derivation, we did not say X has to be this, X has to be that, X has to be unitary, nothing, right? Anything. So, now I am choosing to my advantage a particular form of X that will help me get to great orthogonality theorem. Okay? And I choose this kind of X. I make everything 0. Of course, if we make everything 0, then we might as well go home. We have null matrix, right? Everything but 1. Okay? So, I want to work with an X matrix such that Xij equal to 0 unless I equal to k, j equal to m, and xkm is equal to 1. You could have made it 5, it does not matter. Okay? It is just 1 is the most convenient number. Okay? Do we all agree that even if I write my x this way, I do not lose out one bit on the generality of the situation? I am fine. Right? See, all I care about is that A has to be equal to lambda E. And what we have done so far is that it does not matter which form of X you use, unless X is a null matrix. A is still going to be equal to lambda E. It is just that the value of lambda will change, isn't it? I can use any matrix. So, I choose to use this matrix, which is really 1, 1, and everything else is 0. So, what is the advantage of using this? You are working with a sum, isn't it? All those terms except 1 is going to become 0, right? When you work with the sum, A equal to sum over S ds x ds inverse, I do not need a sum anymore, isn't it? All I have to ensure is that I do not have to in fact worry about anything, because I have only one in x. Okay, even then I have not lost on generality. Let us see now. Okay, now, okay, so far so good. What kind of x are we working with? Xkm equal to 1, k is specific, m is specific, right? Everything else is 0. All other matrix elements are 0. diagonal, off diagonal, everything is 0 except one diagonal element. Okay. Now, and then I say that A is equal to, in any case that A, we said that A equal to lambda E, but lambda is going to depend on x. Here we are choosing a very specific kind of x. So, this lambda also we call lambda Km. Okay. A equal to lambda Km E. That is what we are going to work with. Now, let me write the expression of A. A equal to, as we wrote earlier, sum over S ds x d S inverse. Okay. Now, what is the matrix element Aij? Aij then is going to be, let us say, d ik s multiplied by, sorry, let me call it dip s multiplied by x pq multiplied by d qj S inverse sum over S sum over P sum over Q, right. That is the that is from the straightforward rule of multiplication of matrices, right. And now the nice thing is xpq equal to 0 unless p equal to k and q equal to m when x km equal to 1. What happens then? I still get to write the matrix element on the left hand side, but instead of 3 summations, I can work only with 1 summation, right. Sum over S is the only thing that I need to bother about. What I do is I write d, p has to be equal to k, so I write d I k s multiplied by d q j d m j S inverse. And I do not have to write anything in x anyway, because the only non-zero element is 1. Okay. So, I am left with a very simple summation, right. So, do not forget that A equal to lambda Km multiplied by E, and now we introduce our Kronecker delta. What is Aij? Aij equal to lambda Km, will you allow me to write delta Ij? See, we are getting there. We already have one of the Kronecker deltas. There are 3, we have at least got 1. Got it? Okay. I do not need you to remember everything. What I need you to understand is how we get to the deltas. We get to the deltas by getting at unit matrices. We get to unit matrices by using Schur's lemma, commutativity. That is all I need you to remember and understand. Okay. Beyond this, nothing is required. Okay, fine. So, this is what is Aij. So, I hope you will allow me to write sum over S d I k s d m j S inverse is equal to lambda Km del Ij. They have removed my ruler. So please bear with my ugly curved non-straight lines. What is the range of I? What is the range of j? I goes from 1 to n, j also goes from 1 to n, isn't it? Okay, so I have got 1. Let us see if we can get one more. What are the three deltas we had? One was mu nu. Can you guess how we are going to get that delta mu nu or delta nu mu, whatever you call it? We are going to get there by using the Schur's lemma number 2. If you remember, Schur's lemma number 2 is what correlates two different irreducible representations, right, of different dimensionalities also. Okay, that is where this mu nu will come from. I don't even want to get that far. I'll show you. I'll show you the book. You can do it yourself. But let's do the other one. Okay, so to do the other one, what I need to do is, first of all, I have to get to the deltas one by one. I have to get rid of this one. If I want to get to the km, delta km or delta mk, whatever you want to call it, first I have to get rid of delta ij, then it will become a little simpler. How do I get rid of delta ij? By setting I equal to j, right? Can you set I equal to j and see what you get? Just instead of j, you write I. What do you get? It's not very different. Sum over s, dik s, dmi s inverse is equal to lambda km, isn't it? Okay. I can write sum over s dik s dmi s inverse is equal to lambda km. I do not have to write delta ij anymore because I have said I equal to j. So delta ij is 1. Okay. Now what do I do? I need to get to this delta km somehow, and the only way of getting it to it is to do another summation. Let us sum over I. What do you get? I hope you don't mind me writing sum over s outside, it is fine, right? They are interchangeable. Sum over I equal to 1 to n dik s dmi s inverse is equal to how much? See, this left hand side equal to lambda km is true for every value of I, isn't it? How many values of I are there? N values of I. So I think even my 7-year-old younger son will tell me then that if you sum it over I also, then right hand side gets multiplied by n. Right or wrong? See, it does not matter what the value of I is. The value is lambda km. Now put I equal to 1, you get lambda km. Put I equal to 2, you get another lambda km. Put I equal to 235 if it is required, you get another I equal to another lambda km. So it is n multiplied by lambda km. Okay. Now let us see if I can simplify it a little bit. So what I notice is Ik and Mi DIKS, DMI S inverse. So if I just write it in the opposite sequence, it might be a little more easier to see what that means. So what I am saying is sum over S, sum over I equal to 1 to n. I will just take this forward, I will take this here, DMI S inverse DIK S equal to n lambda Km. What is this? Not the political party. DMK of which matrix? This gives me DMK of S inverse S, a very complicated matrix because you are multiplying a matrix by its inverse. What is S inverse X? You see. So, sum over S, sum over I equal to 1 to n DMK E equal to n lambda Km. So, what will that be? How do I write this? DMK E. Do I not write it as delta MK? Huh? I can write it as delta MK, isn't it? So once again, we have got our unit matrix. That is all we need to do here. Get to a unit matrix, and you get your Kronecker delta. So what I can write is, I can write n lambda Km is equal to sum over S delta Mk right, and that is equal to G delta Mk. You are summing over S, right. So finally, the expression that we have got, if you combine the two, is 2412 sum over S DIK S DMJ S inverse is equal to G by N delta Ij delta Km. Okay. Now you invoke Schur's lemma number 2. You are going to get the third delta also. So I don't want to go there because some had at least come at 5 o'clock, it is almost 7. It is the last class, you are going to have end sem very soon. So I stop here, right. It's been a wonderful experience teaching you. I had a lot of fun. I hope you had some as well. You have done well in mid sem. Do well in end sem as well, even though it is false god, right. It still feels good, right. That will be all for this course. Thank you.